Okay, so we learned a lot about our own star, the sun, and that's definitely going to help us figure out some other things about those hundreds of billions of stars out there. Remember how it would take about 3,000 years or more, right? If we were to just count all of the stars out there. But maybe now we are going to understand a lot more about them. Maybe about how big they are, how luminous, how hot, what's, the amount of matter that they're made of, right? How far away they are. Yeah, and later on, maybe we're going to find out about what the stars are made of. So in this first little lecture, we're going to address their luminosity, basically how much power output they have, and we'll see how that is related to how far away they are. And we're going to leave for the next few sessions figuring out how big or hot or massive they are. Get started with that. Here's a beautiful image from Hubble Space Telescope of a cluster of stars. That's not what's important here, but it's just a bunch of stars. A large bunch of stars. And that is a beautiful image. It's obtained from the space with really high resolution, so it's a sharp image. And of course, you look at them and you see different types of stars, different colors, right? You probably distinguish some are redder or bluer than others. And you also see that some of them seem to be brighter than others. All right, so now the brightness, or what we see or measure here on Earth about the stars, right? That's going to depend on both how far away they are and their intrinsic power output, right? So this is what's emitted at the surface of the stars, right? Let's develop this a bit more here. So what do we have? Luminosity. Let's define some terms. So luminosity is the total amount of power a star radiates, right? So it's again an intrinsic property. It's what the star does, what the star emits from its surface. And it is a measure of power, right, which is energy in time. And so the units are going to be joules per second, or watt. 1 joule per second. Joule per second, which is a watt. Okay, so that's one thing. It has to do, again, with how much power is emitted, that is, at the surface of the star. The other one is the apparent brightness, that is, what is measured, what reaches the Earth, what is measured at surface of Earth by us because we live on the surface of the Earth. Okay, so that is going to be not just the energy per second, so that is power again, but that is going to be power per area, per square meter, right? So the units are going to be joules per second per meter squared, or watts if you want per meter squared. Remember that? 1 joule per second. That is going to be the 1 watt. Okay, so as you can see, these are different things, right? I mean, this is where we are, and we measure things, we look at the faraway things, and of course this is not the scale, right? Especially this little person here, and we look up, but we measure obviously just one part of all of the power that is radiated by the star, right? So here's one question. There are two stars that have about the same luminosity. Again, total power output, intrinsic, like at their surface. At their surface. These are the stars, Alpha Centauri and the Sun. Can you tell which one appears brighter to us? It's obviously the Sun, right? Because Alpha Centauri is much further away from us. But intrinsically, they are actually pretty identical, okay? It's like you have two lamps, identical lamps, but you have one very close to you and you have another one at the end of the street, right? Some few hundred meters away from you. To your eye, obviously the one that is closer to you is going to appear much brighter. So to help you understand maybe even better this idea, here is actually how one way we can actually quantify the relationship between the luminosity and the brightness. Okay, so luminosity, that is whatever is emitted from the surface of the star, and at a distance of 1 AU where we are, so this would be Earth, for example, right? We're going to see a brightness that is basically luminosity divided by the total area of a sphere that has the radius, that is a squared, by the way, right? So area sphere is 4 pi r squared, okay? And the radius, it's obviously, so radius is actually the distance from us, right? So it's 4 pi distance squared. So this is going to be the brightness. Okay, look for example at where Mars is. So about 2 AUs, right? So say, okay, this is where planet Mars is. It's going to be at a distance that is twice as far away we are from the Sun. Okay, so the radius of that surface is going to be double, right? So basically from Mars, the Sun is going to appear weaker. How much weaker? By a factor of 2 squared. So to summarize, here are the formulae we wrote in the previous slide. So again, this is distance squared. I'll write it again for you. So luminosity, it's 4 pi distance squared times brightness. Or this one, brightness. And it's the same formula. You just turn it around and solve here for luminosity, right? So L luminosity is going to be luminosity divided by 4 pi distance squared. Okay, let's apply that formula because it's important to know how. So say by magic that star Alpha Centauri would be 3 times further away. So we have new distance is 3 times old distance. What's going to happen? What would happen with its apparent brightness? So remember, brightness is luminosity of the star divided by 4 pi distance squared. Okay, so we have all brightness, it's going to be all distance. How about new brightness? It's going to be obviously the same luminosity because intrinsically nothing happened with the star, okay? So we have same star, so old luminosity is the new luminosity, right? Nothing happened with the star, so it's going to be the same luminosity. Now we have the new distance squared. But we have the information about what happened with the new distance, so let's plug it in. So we have luminosity divided by 4 pi, and the new distance is 3 times old distance squared. And remember, we apply the formula a times b to the power of 3 or 2. Let's do 2 here. So this is a squared times b squared. So we're going to apply this idea. So we have L divided by 4 pi, and then we have 3 squared times distance squared. And this is all distance. And we can separate this one. We're going to take it outside, so it's going to be 1 over 3 squared. And then whatever is left is L over 4 pi distance squared. Again, all distance. Forgot to write. But look at that. What is L luminosity over 4 pi distance squared? All distance squared. That's going to be the old brightness, right? So what do we get? If we continue here, it's going to be 1 over, this is 9, okay? And it's going to be old brightness. So this is our result. This is how we started with. So new brightness is 1 over 9. This is 1 over 3 squared, and that's the factor by which the distance changed times old brightness. So this is the result. And to answer our problem, right, how would the apparent brightness of the Alpha Centauri change if it were 3 times further away? It would be only 1/9 as bright. So that's how you would find the correct answer in one of the problems in Mastering Astronomy, 1 or 2 or more. Okay, so as you have seen so far, it's actually very important to know how far away these stars are, to know the distance to the stars or any other cosmic object out there. In order to know intrinsically how luminous they are, all we need to know is how far away they are, and then just the measurement of how bright they appear to us, and then we're going to find out intrinsically how they luminous are. So remember, that's the formula. So we have 4 pi distance squared times brightness. So again, without knowing how far away they are, we're not going to know intrinsically how they are. And remember about the parallax. That's one way of actually figuring out how far away stars are, especially actually for the nearest stars, okay? Because the parallax angle, which is basically this angle here, so remember this is the nearby star, this is the Earth in December, and this is where the Earth will be in July, right? And remember this is 1 AU, 1 astronomical unit. That's the distance, average distance between Earth and the Sun. All right. So this is where you see basically the star in December, and then this is where you would see the sun in July. Those are like with respect to the distant stars, right? And the parallax is this angle. Okay, so we're not, without going into the like trigonometry or the calculations of this. So this is P, it's an angle. This is a right triangle. This is the distance, and you have here another side of the triangle that you know. You can calculate, so knowing or measuring, which is easy to measure, right? It's just an angle P, the parallax. We can calculate distance. But again, that's true of the nearest stars, right? If the stars are far away, P is very, very small. So basically, hard to measure. Okay, so yeah, we can get distances by measuring parallaxes for the nearby stars, which, you know, it works. So we get distances and we get the brightness, and this would be L sun, right? So something like L sun, the luminosity of the sun. That's a new unit here, right? So we have L sun, it's an index. And so we get to measure the luminosities of the stars, and this is the power of 6, and this is the power of -4. So the least luminous stars are basically 1/10,000 times the luminosity of the sun, and then the most luminous suns, they are 1,000,000 times, oh gosh, kind of like that, right? Okay, more luminous than the sun. So you get about 10 orders of magnitude in luminosity for all the stars out there, which is pretty vast range of how luminous intrinsically the stars are.